evening, everyone. I am Alan Mannoosseril, and I'm from the James Watt School of Engineering. I have a background in aerospace engineering, but I'm here at the Infrastructure and Environment Research Group. And today, I'll be talking about uncertainty quantification in structural mechanics and how we use random matrices to quantify it. But before that, let me tell you a story about an exploration vehicle. This was made by a group of innovators. It had many successful trips. Its funding was supported by Boeing Research and Technology and the Applied Physics Laboratory at the University of Washington. But on a fateful day on 18 June 2023, it suffered a catastrophic failure. It was operated by a company called OceanGate. Some of you might know what vessel I'm talking about. It was the Cyclops Titan submersible, which went on to probe the Titanic shipwreck. Well, we all know what followed the 5 days when the search continued. It was commentaries filled on social media, internet, news outlets, and scientific communities about how this was a disaster waiting to happen. Now, thinking back at it, now since the disaster has happened, it's very easy to say that, oh yeah, you should have done like that, right? But have you ever thought how engineers make all these structures safe and reliable even before they're tested? So, one of the ways that we do is experimental testing. Obviously, it is the inevitable way. We have to test any product before we release it. But as you can see, it is very resource intensive. Cost is very high, and it's also time consuming. Also, for example, a SpaceX launch would cost billions of dollars. And we have to make sure the launch is perfect before we even launch it. So how do we do that? How do we test a model even before we have it? We could make a prototype. Again, that's expensive. So we resort to computational models. But what exactly is computational models? Are these mere drawings of a prototype on a piece of paper or in a computer? It definitely is not. Is it a 3D representation of a model? Definitely not. But actually, a computational model is where it captures the physical reality of any structure. That means it obeys the laws of physics and behaves exactly as it should behave in a real condition. Well, that solves all the problem, right? We could create computational models and solve all our uncertainties. We have all the results, but not so much, because there are so many uncertainties in here. So what are the uncertainties? Depending on the type of surroundings the system interacts with, there can be changes in the structure, depending on the different types of parameters or the quantities or the behavior of the material. It can have loads and loads of changes. How do we quantify all these changes? In earlier days, we used to take one of these parameters, calculate the different values that is possible for this particular parameter, quantify it, do the analysis one by one. That takes a lot of time. Is there some way we could quantify all the variations of these parameters simultaneously? So that's where random matrices comes in. But before telling you how I use random matrices, we need to know a little bit of finite element method, or the thing that we use to divide a whole structure into tiny elements which are connected by nodes and analyze the response of a whole system. The speciality of this method is that each of the elements has the effect of the force or the boundary condition that is acted upon it. And there's something called the stiffness of an element, which is how much it would displace based on the force acted upon it. And it is interesting that stiffness is always represented as a matrix with a lot of different variables, which include all the material, shape, size, dimensions, and the properties in it. When we simplify it, it narrows down to a simple equation, depending on the systems, but this is for a simple system. And what basically a computer does is solve this equation and give us the response. And this is where the stiffness metric comes in. To understand how the stiffness matrix is and how big it can be, let's look at a simple system where there are 3 elements. So each of these elements have a stiffness matrix, and it is assembled as a global structure, and it becomes a large matrix. But this is for a simple 3-element structure. So now, any changes in these materials, maybe it's a crack or like one of the elements is missing, it would change this matrix. So that means if you randomize this matrix, we could get all the different realities of a structure, and that could quantify all the uncertainties. So that's exactly what we're going to do. We're going to randomize this matrix. But this is a small system with just 3 elements, and the matrix is very small. But the model I showed you before had thousands of elements. And if it's an aircraft, there are thousands and thousands of elements. So the matrix would be large, but it's creating different realities, and it would be much, much larger. So what exactly are we doing here? We are creating different realities or different simulations of probably not the real world. So we are not very far advanced as like this. We are not yet there to create different realities of world like in the movie Matrix. But what we get is probability distribution curves. From these distribution curves, what we get is like instead of a singular value or the outputs, we get a range of values, or from which we can estimate the extremities or tolerances of these values based on the dispersion levels that we set. So by doing this, we could have analyzed that, probabilistically speaking, if the tolerance were given, going into the depths of Titanic shipwreck with that particular model and particular materials would have been catastrophic. Well, ironically, even I am saying that after the destruction has happened. But my job is to quantify and collect data for more different types of structures and materials and refine this analysis process so this wouldn't happen in the future. So we may not be able to generate a reality, a simulated reality of our world, or quantify the uncertainties of our life, but as engineers, we can certainly quantify the uncertainties in structures, and that's how we make the world a little bit more better. Thank you, and that's my time.